Before we have a look at this example, we're going to have a look at two key facts that we need to know. So the first one is just a quick reminder about proportion and inverse proportion. So we know that if y is proportional to x, then we can write that y equals some constant, we normally use the letter k, times by x. And k is called the constant of proportionality. And it's important that you realise that you could replace x with x squared, and that would just mean that y equals kx squared. And you also need to know that if y is inversely proportional to x, then we can say that y is equal to k divided by x. And again, we can replace x with any function of x. So for example, if it said y is inversely proportional to root x, then we know that y equals some constant k divided by root x. The second thing that you need to be aware of is what we mean by rate of change. So let's say, for example, that capital P represents the population of a town. And what do we mean by rate of change of P? Well, what we could mean is the rate of change of P with respect to anything. We could be wondering, how does P change with temperature, for example? Or how does P change with the economy, or how the economy is doing? What we mean if we don't say with respect to something is what we really mean is with respect to time. So if you were to draw a graph of the population over time, t, let's say t is days since the start of the year, the graph might look something like that. So what we mean by the rate of change of P at a particular day, say 200 days into the year, is actually the gradient of this graph. And we know that we can write that as a derivative. That's dp by dt. So dp by dt literally means what's the rate of change of population with respect to time. So in this example, a scientist is putting some bacteria on a petri dish and recording the amount of bacteria over time. And we're told that the growth rate of P is proportional to P. So let's deal with this sentence to start with first. So the growth rate of P, what we really mean by that is, how does P change with time? What's the rate of change of P with respect to time? So we know that we can write that as dP by dt. And we're told that it's proportional to P. So this is equal to some constant k multiplied by P. So the key thing to realise here is that the growth rate of P is the rate of change of P with respect to time, so dP by dt. And you'll notice that this is a differential equation. So this is going to be really useful. You're always going to start these questions by forming a differential equation with a derivative in. And almost always the first part of the question will be solving this differential equation to find out what is the population in terms of time. Next, I'm going to look at the next sentence and write down what information we've got. So we're told at the start of the experiment there were 100 bacteria. So we know that when t equals 0, P equals 100. And we also know at the start of the experiment that P was growing at a rate of 50 per hour. So that means that when t equals 0, dP by dt, so that's the growth rate, was equal to 50. So that literally means that if we were to draw a graph of P against T, that, I don't know, the graph is going to look something like that, that we know that when t equals 0, P equals 100, and we're also told that at that instant, at the start, dP by dt, the gradient of this tangent, is equal to 50. So normally what we'd do is we would just solve this differential equation, but there's a bit of a trick for this question because we can actually find out what this value of k is equal to. Because we know that when t equals 0, that P equals 100 and dP by dt equals 50. So we know that when P equals 100, dP by dt equals 50. So we can sub in dP by dt equals 50 and p equals 100 into our differential equation. So we know that k must be equal to 50 divided by 100, which is a half. So we know that dp by dt is equal to a half p. So in part A, we're asked to find an expression for p in terms of t. So basically we want an equation which involves p and t, but without dp by dt in it. So we know that we're just going to solve this differential equation just like we did in the previous section of this chapter. So we're going to use the method of separation of variables. So I'm going to times through by dt. So I'm going to have dp equals a half p dt. And then I'm going to divide both sides by p to get all the p's on the left hand side. So we're going to have 1 over p dp equals a half dt. And now I'm going to integrate both sides. So on the left hand side I'm going to have natural log of p. And I know p is always positive, so I don't need to worry about the modular symbols, but I could put the modular symbols there. And I'm going to have a half dt, a half t. And I'm going to remember my constant of integration on the right hand side. So I can rearrange this or I can simplify it because I want p in terms of t. So I need p the subject. So I'm going to have p equals, I'm going to do e to the power of both sides. So e to the power of half t plus c. Now we could leave it like this and we could find out what the value of c is, but often we don't write it like this. If inside the power you've got plus c, what we normally do is we split this up into e to the power of a half t times by e to the power of c, because we would add those two powers together and get back to what we started with. Well, e to the c is just a constant. So we might as well say e to the c is equal to some other letter, and we often use the letter a because c is just a constant, so e to the c is just another constant that we're trying to find. So we could actually write that as p equals a e to the half t. Now you'd be absolutely fine if you didn't rewrite it like this. You could still find out what c is, but it makes it a little bit easier and a little bit neater. And this now matches what you've done in last year with exponential functions. So finally, we need to find out what this value of capital A is. Well, that's not a problem because we know that when t equals 0, p equals 100. So at this point, I can sub in 100 for p and t equals 0. So we'll have a e to the 0. E to the 0 is just 1. So we know that a equals 100. So we know we can write p equals 100 e to the half t. Now I mentioned at the start that we had a bit of a trick to find the value of k because we knew that when dp by dt was 50, p was 100. If you didn't do this trick, you'd be absolutely fine because at this point, once you found an expression for p, you would just have, instead of a half there, you would have k. And then all you'd need to do is differentiate this to find dp by dt, and then you would be able to find an expression for k. So in part B, we want to find the size of the population 8 hours after the start of the experiment. So 8 hours after the start of the experiment, we know that that is when t equals 8. So all we need to do is sub in t equals 8 into this expression. So when t equals 8, p equals 100 e to the half times 8. So we're going to have 100 e to the power of 4. And that's going to be 5,459.81. Now we're talking about bacteria, so it doesn't. We might as well round to the nearest whole because that makes sense for bacteria. So 5,460. And for C, we want to find the values of t for which p is greater than 1,000. So all we need to do is put p is greater than 1,000. So that means that 100 e to the half t needs to be greater than 1,000. So we're just going to solve this inequality. So I'm going to divide through by 100. So that means e to the half t needs to be greater than 10. And I'm going to do logs of both sides, natural log of both sides. So on the left hand side I'm going to have a half t is greater than log 10. So we know that t has to be greater than 2 log 10. Well, 2 log 10 is 4.6 1 to 3 sig fig. So that means that the population gets more than 1,000 at 4.61 hours into the experiment. And then for D, state one limitation of the model for large values of t. Well, if we look at our expression for p, if you put in a large value of t, it's going to get larger. And if you think about what the context of the question was, we were growing bacteria in a petri dish. A petri dish only has a certain amount of food or a certain amount of space, so it doesn't make sense that as t goes to infinity, that the population of the bacteria is going to go to infinity. So all you need to do is say the petri dish will run out of space, so p won't get infinitely large.